This is the next section of the Maths for Computing course, and this is trees. Now, a lot of concepts in this follow on from a previous section of the course, Introduction to Graph Theory, the ideas of vertices and edges and so on. Now, the three parts of of this particular section of the syllabus are as follows: properties of trees, rooted trees and binary trees, and then, last but not least, binary search trees. Binary search trees are a very important idea in computer science, particularly computer hardware applications, and memory and stuff like that. And also, database is actually more to the point. So, let's begin by looking at a few topics or a few definitions. Characteristics of a tree. This is actually an important definition and gets asked a lot. So, a tree is a connected graph, okay, straightforward enough, and it also contains no cycles. So that is actually one of the two key components of what gets asked. The other things you would need to say is this is sort of a very succinct but reasonably good definition of what a tree is in terms of mathematics. A tree has no loops and no multiple edges. All trees are simple graphs. So that is a fairly robust idea about what a tree is. Now, important, quite a useful definition to know is also a path graph. And a path graph is a tree that only contains vertices of degree 1 or 2. Okay, and the length of a path is the number of edges in it. Now, let's have a look at this. It actually might make more sense if you actually draw out a path graph to get a sense of it. So let's say we have one there with 5 vertices. A path graph is essentially a path between all of those vertices. Okay, and you can see very quickly that the number of edges is either one at the end, but otherwise 2 in the intermediate vertices. So that's the idea of a path graph. The length of a path graph is the number of edges in it. Here it's, let's say, give them call them A, B, C, and D. Give them alphabetical names, and there are four edges there. Okay, so this is an important, handy little definition. It's 3.3 from the study guide. Let T be a tree with n vertices, then therefore T has n minus 1 edges. So if there's 6 vertices, that means there's 5 edges. Straightforward enough. Now, these are 3 important definitions. So first off, a subgraph. First off, let's just look at what a subgraph is in its own right. If H is a subgraph of a graph G, if that is the case, if it's a subgraph, the vertices of H are a subset of the vertices of G, and its edge set are a subset of the edge set of G, and each edge of H has the same n vertices in G. They're both the same in G and H. Sorry, that's not necessary. I re-edited that. So, just looking at a subgraph first, let's suppose that this is a graph G. So, let's connect it, draw it up here. Very simple graph like this, and this is the edge set of G. Something like that. Actually, just as a remark, it doesn't have to be a tree. Okay, so suppose that, actually, you know what, I'll make those red, vertices red, just to make it a little bit easier to read. Okay. Now, let's draw in a subgraph of G, and let's put in the colors in blue. So essentially, some set of vertices picked out, and some set of edges. Okay, so that's the idea of a subgraph. Now, if the subgraph of H has to contain edges, has to use edges that are part of G. So you can't have something like this. as part of the subgraph because it's not an edge in G. It's not part of the. It's not a part of the edge set of G. So that's not allowed. That part there. So a spanning subgraph of G is if the vertices of H are the same as the vertices of G. Now up here we have a subgraph, but it's not a spanning subgraph, and the reason is this vertex here is not connected with H. So essentially now it becomes a spanning subgraph of G. If H is a spanning subgraph of which is also a tree, then H is said to be a spanning tree of G. G does not need to be a tree. Now, one thing there is do we have a tree there? Okay. So let's just sort of check for a second. Does that constitute a tree? Well, it's simple, connected, there's no loops, and there's no cycles. So yeah, that H there is a tree. Now, like previously I talked about path cycles, or path graphs. Doesn't have to be a path graph. Okay, so that's spanning trees and spanning subgraphs. Now, spanning tree is the main component of this lesson. Now, one thing we're going to do here is a quick exercise. We're going to draw a graph. This is from the 2008 paper. We're just going to have a hell of a blast at this, and then we'll wrap it up for this video. We'll only do these two first sections here in this particular video. So first off, let's draw our vertices. Draw them in a sort of anti-clockwise fashion. For some reason, that's the pretty usual. Let's connect them up now. A is connected to B and E. B is connected to A, C, and D. C is connected to B and D. Okay. D is connected to B, C, and E, so we just have to connect it to E. And E is connected to D and A. That's grand. That's the draw of the graph G. Now, draw a spanning tree of G. Well, what we could do there, we're going to put it in green. Let's draw a path graph through it. There, like that. That would constitute a spanning tree of G. Now, I'm sort of doing this on the same... Oh, I'm superimposing it just for the sake of space, but it's probably a good idea in your exam sheet to just do it out again separately. It looks a bit better, like when you're trying to shoot... I'm only doing it this way partly because of the consideration for space. Actually, draw all the non-isomorphic spanning trees of G. Well, I'm going to draw another spanning tree quickly that is not isomorphic to the one we have. So this one's a path graph, as you can see pretty clearly. So all I have to do is draw a spanning tree that has... we can have one that where there is a vertex of degree 3. So what I'm going to do is actually use this one here. We'll go down here, then go over here, up here. Now, I have to add in one more vertex. I have to add in B. I have to connect to B. Now, if I connect from A, I have basically a graph, a tree that is isomorphic to the one I've drawn previously. Likewise, if I go from C, it's isomorphic to the green one I've drawn previously. What I could do is actually draw from here. Necessarily, this is not isomorphic because here, for the second one I've drawn, we have a degree of 3. Okay, whereas the other two options would have been path graphs. Anyway, that's quite a bit of work there. That's actually what you have to think about when you draw all the non-isomorphic spanning trees of G, but it's worth a separate video, so I'll stop it there.